Hey, how are you? Today we're going to talk about piecewise functions and continuity on intervals. So, in this example, we have a graph. You have your x-axis and the y-axis, okay? Now, why is this graph important? Well, you might notice something. There is like a hole in this line. Now, this line is just simply a linear function. And we know since, well, it begins at the origin that it has a y-intercept of 0. So you can just simply say that this line is equal to, well, is y is equal to x, basically. This is the line that we have. However, there is something special to this line. We do not want to have any outputs when x is between 2 and 3, okay? Now, how do you write this in terms of more mathematical notation? Well, this is what we call, for example, a function on intervals or a piecewise function. When you have a function that's, in this case, before or, well, in the interval from 0 to 2, we have outputs, just as they normally would go out. But between 2 and 3, we do not want any outputs. We call these pieces, or, well, the intervals in a piecewise function. I'm going to show you what I mean by that. So if we say that this function is going to have two pieces, the first piece is going to be this first line, okay? Now, we know it's just simply going to be x, and we're going to place a comma to specify when we want this function. So we're going to say when x is less, well, now, in this case, this first piece would be when x is less, including 2. Is less than 2, including 2, okay? So how does that look? Well, it looks like this, x, 2, okay? We say, you can see maybe these little circles, or these like dots. These dots, they just simply mean that we could make, for example, if you had a line like this, and you say that there's like a spot right there, you say that at 5, you do not want to include the number that is in there. Okay, so for instance, this would be the interval of the numbers between 4 and 5 without including 5, because it's empty. However, if we have a circle that is complete, or yeah, if we have like this, if we have it like this, well, that just simply means that we have x can be equal to 2, okay? Because when we have 2, well, we have an output right there. So that's what this little ball means. So now, this is our first piece. So we have x, this is going to be a line that represents x, okay? This is our function, and we're going to say with these, with these brackets, that there are two pieces or two structures. The first one is going to be, once again, x, a line that is going to be the same output, or that is going to output the same thing that we plug in, and that is going to happen. You can say this function happens when x is smaller or equal to 2, okay? And that would be this line. Now, what about this second line? Well, you can probably see that this line happens when x is greater than 3 or equal to 3, because we have a, like a complete circle. So you can say x is going to be this first piece. It's going to be first piece. And now the second piece is going to be x, once again, because it's just a line. A slope of 1, intercept of 1, 2, oh, well, of 0. It begins at the origin. And we're going to say this happens when x is greater than 3. Okay, and actually, you're going to see something. So when x is greater or equal to 3, then we want this function to happen. Now you can see there's some sort of hole between these two functions, because if x is greater than 2, then it will not be, if x is greater than 2, then, well, it can also be greater than 3. However, we cannot let x be smaller than 3. So that means that we cannot have any number between 2 and 3, which is exactly what happens here. So you could say that from the interval 2, without including 2, so in this case, we do not write the equal, we just write the inequality. So when x is greater than 2, but it's smaller than 3, then we want, you could say, no function. Okay? Which is exactly what is going on in here. You don't have any line, you don't have any outputs. Okay? And if you don't have any outputs, well, that happens because you say that when x is greater than 2, so from this point on, but when it is also smaller than 3, so from this point backwards, we do not have anything. We do not want anything. So we have three pieces, you could say, or well, three statements that make up this function, okay? Don't try to see this as the notion of, well, a function. It's just simply going to be, well, f of x is equal to x squared, and that's it. You know, you have an output, and then there's an input, and that's it. No, no, no. Try to expand your notion of a function as to something that has different statements or different conditions. We have that we want a line that is going to be x when x is smaller or equal to 2. And we want a line that is also going to be x when x is greater than 3 or equal to 3. And between 2 and 3, we do not want anything, okay? Now this is like the main notion of intervals, and there is something pretty cool with continuity. So we know the definition of continuity, I'm going to do this with blue, is going to be the limit as x approaches any value a from the right side should be, well, for the function f of x, should be equal to, first of all, f of a, and also, it looks bad, this is f of a, and also it should be equal to the limit as x approaches a from the left side, okay? So if we have this, now this is the continuity definition. You can grab this definition and plug in some information from this graph into this. So let's say our point is going to be, let's say we choose, for instance, 2.5, okay? So this will be 2.5, and this is going to be our point A, okay? 2.5. So if A, I'm going to write it here, A is equal to 2.5, then we can say that what happens if we take the limit as x approaches 2.5 from the right side for the function f of x. How much is f of x? Well, we know it's just simply x, okay? F of x is the same as y. So we have for the function x, and this should be equal to f of 2.5. And it should also be equal to the limit as x approaches 2.5 from the left side, okay, for the function x. Now, this limit, first of all, what you want to check is that, well, we know I have a function. And can I try to plug in 2.5 into that function? Well, we need to go back to our statements. Now, we know 2.5 is between 2 and 3. And 2.5 is not smaller than 2 or greater than 3. So these two conditions, don't think about them. Think about this one. 2.5 is between 2 and 3. And we said that in this interval, we do not want any output. We don't want any function. We don't want anything. Okay, our graph is going to have a hole in this interval. So that means that this limit doesn't have a value. It doesn't exist. So just right off the bat, if this doesn't have a value, or well, you can't really define it because you don't have any output for this number. Well, first of all, you could just simply say that this equation is not true at all and is not going to hold. But also you could say that, well, f of 2.5, how much would that be? Once again, you could say that since 2.5 does not qualify for any of these statements, because it's smaller, it's greater than 2 but smaller than 3, then we need to put it in somewhere else that is not determined by these two statements, which are the only statements that have an output. This statement is the only one with a, well, that includes the numbers between 2 and 3. And f of 2.5 would lie in this statement. And since this statement says that we don't want any function, and that means that we don't want any output, then we're not going to have any value for this either. And it happens the same thing here. Even if you go from the right side or the left side, if you don't have any statement that treats or that knows how to deal with this number, then you don't have any value. And if you cannot prove that this equation is true, then you say that the function is discontinuous. So f of x is discontinuous, all right, disk, at x equals 2.5, okay? And now you know why that is true, because 2.5, well, doesn't really qualify for these two statements, but it qualifies for this one. And what does this statement say? Well, we don't want any outputs, okay? And graphically, you can see that. If you go between 2 and 3, well, you can see here that there's nothing. So you're not going to be able to put any number. And real quick, if you think about what would happen if we said, what if we say that A, in this case, using the continuator definition, A is equal to 2. Let's try that. So if we say the limit as x approaches 2 from the right side for the function x should be equal to f of 2, and should also be equal to the limit as x approaches 2 from the left side for the function x, okay? Now this should be true if the function is continuous. So if we go from the left side first, so from values smaller than 2, well, we can see that the limit is going to be 2. So I'm going to write this. So this limit is going to be 2, right? And it also works in the conditions because, well, we want values that are smaller than 2. So, and x in this statement is smaller than 2. So you can write 2 in this side. Now, this f of 2, we also know that it's defined because we are including 2. So it should go on this side. Well, it goes, I mean, you can see a line, it goes to 2. So we're also going to write this is equal to 2. Okay. These two guys, they are true, they hold. But what about this one? What happens as we approach 2 from the right side? Or from values bigger than 2? Well, since we know that any value bigger than 2 has no value or no output, no function, well, then that means that this limit, well, we cannot really find what it is. Because if you go from any number greater than 2, you can see that you don't have anything, okay? It's empty. There's nothing. So you cannot have this limit because as you approach x, as you approach 2 from values greater, well, you have nothing. So basically, this limit is just simply, you could say undefined or undetermined, or you simply cannot find it because of your statements, okay, or your pieces. This is a piecewise function because you have 1, 2, and you could say this is like a third piece, but it's not, but you can understand it like that, okay? So I hope this has given you some notion into intervals and piecewise functions, and of course some continuity. So, well, this is pretty cool. It's just, you know, some introductory calculus. There's some more advanced things. But yeah, this is pretty cool. So I hope you enjoyed this video, learned something, and see you in the following one.